we know that a matrix is diagonalizable exactly when there's a basis for Rn consisting entirely of eigenvectors for that matrix. But that doesn't really tell us how to find the corresponding diagonal matrix. But actually, the proof of this fact does give us a recipe for finding the diagonalization of A. Right? So when we proved this fact, remember what we did was we had this matrix P, whose columns were the eigenvectors of A, and we had this diagonal matrix D, whose diagonal entries were just the eigenvalues. So lambda 1 through lambda n are eigenvalues for A. And they might be repeated, right? Since the way we have this notation set up, each eigenvector corresponds to the eigenvalue in the same position. Okay. Well, this actually gives us a recipe for diagonalizing a matrix. All we need to do is find the eigenvectors find all the eigenvalues for A, put them all into a diagonal matrix, find the corresponding eigenvectors in the same order, put them all into a matrix, and that tells you how to diagonalize A. And this is something we can do. It's just a matter of finding all the eigenvalues and eigenvectors, which we already know how to do. So let's try it. Oh, notice also if we've computed this, then we can check that this is correct because if we multiply on the left by P inverse and on the right by P, we get P inverse A P equals D. Right? So we could use this to check that we've done everything right, because once we're done with this calculation and we have all P and D, if we apply this similarity transformation to A by multiplying on the left by P inverse and on the right by P, we should get the diagonal matrix that has the eigenvalues down the diagonal. Or I guess you could just plug everything into here and multiply it all out if you wanted to check. All right, so let's look at a couple examples. If it's possible to, let's diagonalize this matrix. Remember, not every matrix is diagonalizable, and we know exactly what kind of matrices are diagonalizable. They will be matrices that have a basis of eigenvectors. But we were going to find the eigenvectors anyway, so if it's not possible to diagonalize this matrix, we will notice in the course of our calculation. So first we need to find our eigenvalues. So let's see, we need to find the determinant of lambda I minus A. So this is going to be lambda plus 56 times lambda minus 58 plus 90 times 36. So why are these numbers so big? They're so big so that I could have an example that works out the way I want it to. Okay, so now we need to multiply this all out. So lambda squared, let's see, minus 56 plus 56. So minus 2 lambda, and then minus 3,248 plus 90 times 36, 3,240. So lambda squared minus 2 lambda minus 8. Right? Now we want to know when this is equal to 0 to find eigenvalues. So let's factor this. It's lambda minus 4 times lambda plus 2. So we get two distinct eigenvalues. 4, let's call that lambda 1, and lambda 2 is minus 2. Okay, Now, things are looking good for diagonalization. Remember that each eigenvalue has to have at least one eigenvector. So there will be an eigenvector for lambda 1 and an eigenvector for lambda 2. As long as they aren't linearly dependent, which will turn out to be impossible, we'll have two linearly independent eigenvectors, and that'll be a basis for R2. So things are looking good for diagonalizability. At this point, we know the diagonal matrix that we're heading for. Right? It's minus 4, 0, 0, 2. Okay, now we need to find the eigenvectors, or the eigenspaces, for each one of these eigenvalues. So for lambda 1, which is 4, we need to find a minus I lambda, or lambda I, either order. Right, we're going to find the null space of this matrix. So let's see. So a minus 4i, so minus 60, 90, minus 36, and I'm subtracting 4, so 54. Okay, let's see. So let's take some low-hanging, we need to row reduce this, so let's take some low-hanging fruit, and looks like everything is divisible by 6. So we're going to get minus, actually, why don't we divide this first row by minus 30? Maybe that's going to be the easiest way. So we're going to get 2 and minus 3. And then, let's see, second row, divide this by minus 6, I guess. We're going to get minus 6, sorry, positive 6. And then minus 9. Okay, yeah, these two rows are scalar multiples. So this is 2 minus 3, and divide these by 3, 2 minus 3. So then we can row reduce to 0 out these guys. And so a vector in the null space of this is going to be 3, 2. Okay, so that can be our first eigenvector. So that's an eigenvector for the eigenvalue lambda 1. Our second eigenvalue was minus 2. So now let's compute the corresponding eigenspace, or really, we know ahead of time there's going to be just a single, one-dimensional eigenspace, so we're just looking for a single eigenvector. So this is going to be, let's see, what was A? So negative 56 plus 2 is negative 54, and then 90, negative 36, and then 58 minus 2 is 56. Okay, so let's see, first row, let's divide by negative 9, I guess, so 6 and negative 10. And then here, let's divide by negative 6. So 6. And did I make a mistake? Oh, yes, I did. I was supposed to be adding 2, and I subtracted 2. This should be a 60. Okay, good. And that means that this comes out to negative 10. So let's see. Now we can divide both of these by, use these to 0 out those guys, and then divide by 2, so we're going to get 3 minus 5, 0, 0. And that means that an eigenvector is in the null space of this matrix, so that's going to be 5, 3. Right? Yes. Okay. So, this means that the matrix that does the diagonalizing, which we've been calling P, is, right, its columns are just these eigenvectors, so 3, 2, 5, 3. and we're going to need it to check. So at this point, right, we know P, we know D. D is 4 minus 2 down the diagonal. So at this point, we know that, right, assuming we haven't made any mistakes, we know that A is P times D times P inverse. If we want to actually check this, we'll need to calculate P inverse. Or I guess we could check this, right? If we multiply on the right by P, we get AP equals PD. So I guess we could check that we've done this correctly just by doing this product, right? This is going to save us the trouble of calculating P inverse. Okay, I've consulted Sage, and P inverse is minus 3, 5, 2, minus 3. Okay, so let's actually multiply this out just to sort of see the magic happen, I guess. So 3, 5, 2, 3. Right, the more, if you're confident in your calculation, you don't necessarily need to check, but I think it's good, at least the first time we do this, it's good to, see that this actually works. I mean, we know that it should, right? The theory is sound, but it's kind of nice to see the numbers actually work out. So let's see that we can do this product here. So we're going to get 4 times the first column, so that's 12 and 8. And then minus 2 times the second column, so minus 10 and minus 6. And now things get messy. Minus 3, 2, 5 minus 3. So let's see. Minus 36 minus 20 for this upper left corner. So that's going to be minus 56, and then minus 24 minus 12, so minus 36, and then in the right we're going to get 5 times 12, so 60 plus 30, so 90, and then 40 plus 18, so 58. Okay, hopefully that's what we started with. Yes, okay, it worked, good. All right, okay, let's look at one more example. Let's diagonalize this matrix. So as usual, first we need to find eigenvalues. So let's find the determinant of lambda I minus a. So, in this, you can use lambda I minus a or a minus lambda I. Since these two matrices are negatives, their determinants will be either the same or negatives of each other, depending on how big a is. And, whether they're equal or they're negative, they'll have the same zeros, and the eigenvalues are the zeros. So either way, you'll get the same eigenvalues. Okay, so this is, let's see, so lambda minus 2 times lambda minus 0, okay, plus 1. Okay, so this is lambda squared minus 2 lambda plus 1. So this is lambda minus 1 squared. So, right, to set that, we want to know when is this 0, so that's when lambda is 1. Okay. Notice that we get just this single eigenvalue. That doesn't mean this matrix isn't diagonalizable, because the eigenspace associated to this eigenvalue might be two-dimensional, right? We may have a basis of eigenvectors whose eigenvalue is 1, although secretly that's can't be the case for theoretical reasons in this particular example. So, you know, we still have to check in general, especially if this were a bigger example. In general, we would still have to check, is it possible that we have two linearly independent eigenvectors for this single eigenvalue? So, you know, we might have this for our diagonal matrix. Okay, well, let's try it. Let's find the eigenvectors associated to this eigenvalue. So a minus lambda I. So again, you could find the null space of lambda I minus a. These two matrices, they're negatives, but they have the same null space. So, you know, whichever one you prefer. I like to do this one when finding the null space just because I get fewer minus signs coming from a. So this is, let's see, our eigenvalue is 1, so we're going to get 1, 1, minus 1, minus 1. And when we row reduce, we get 1, 1, 0, 0. And so our eigenvector, our null space is one-dimensional, and it's spanned by 1 minus 1. So we don't have a basis of eigenvectors. Right, so for this particular, for this matrix A, there is not a basis of eigenvectors, and so it is impossible to diagonalize this matrix, right? We cannot write this matrix as similar to a diagonal matrix.